using our iterative methods. So, what is initial value problem? So, we'll discuss this thing. So suppose you have mth order differential equation, then we can write the mth order differential equation like this. It means it involves the derivative of the dependent variable up to m order. So the order of the differential equation is the order of differential equation is the highest is the order is the highest order derivative, and the degree is the highest derivative after the equation has been rationalized. So the degree of the highest derivative is known as the degree of the differential equation, and the highest order derivative present in the differential equation, that is called the order of the differential equation. Then we have linear differential equation of order m, can be rewritten or written as like this. So when we say linear, it means that there is no multiplication of derivative terms or y dependent variable together, and there is no terms like derivatives powers like dy by dx square or dy by dx cube. So these kind of terms are not present in the differential equation. Then we say it's linear. So linear differential equation means the derivative, two derivatives terms are not product, like y dash and y2, y double dash product term is not there, and there is no terms like that y dash square or y double dash square should be present in the equation. Then the such a equation is known as a linear differential equation. So here a naught x is can be function of x or can be constant also. So these a naught, a1 up to am and rx are constants and continuous function of x. So if we have this kind of form where a naught, a1, mx are continuous function of x or constant, and there is no product of the derivative term exist, and no higher degree term of like more than one degree term of any derivative exist, then such a differential equation is known as linear differential equation. So the general solution of, because it's a m degree equation, m degree differential equation, because the highest mth order differential equation, because the highest order derivative present here is m, so it has m arbitrary constants in its solutions. So the general solution in implicit form can be written as this: y g x comma y comma c1 c2 up to cn, or in explicit form we can write like this: y equals to hx c1 c2 cn. And these arbitrary constants C1 up to Cm can be calculated by using the specified conditions. Since we have m arbitrary constants, so we required m conditions, and these are the conditions. They can be of other form also. So first we see this one: y of x naught equals to b naught, y dash of x naught equals to b1, y double dash of x naught equals to b2, and y m minus 1th order at x naught is bm minus 1. So here you can observe one thing: all the conditions are at a fixed given point x naught. So if they are on a single point x naught, then such a problem is known as initial value problem, or we can say these conditions are known as initial conditions, because all the m conditions are prescribed at the point x equals to x naught, and such a point x naught is known as initial point, and these conditions are known as initial condition. And if we have this problem, this differential equation with this initial condition, if this differential equation with this initial condition, then we say that it is a initial value problem. So the differential equation 4.2 with the initial condition 4.5 is known as the initial value problem. Then we have the first order initial value problem can be formulated as like we have y dash because first order means first order differential term is exists in the equation, and we have this is as a initial condition y at x naught equals to b naught. So suppose you have a second order differential equation, then how what you will do, you reduce the second order differential equation into a first order system of equations. So how we will do in this, like suppose we have this is a second order differential equation because second derivative of y with respect to x is present here, and it is again an initial value problem. Y as at x naught we know, and y dash at x naught we know. So to reduce is a system in a system of first order system to this given second order differential equation into first order system of, then what we will do, we assume that one variable is introducing the new variable u1, and we say it's taking value y, and then we write u1 dash equals to y1 dash, and y1 dash we assign another variable y2, you sorry u2. So u2 is the second variable. So u1 is the first variable, we have assuming y, and the second variable u2 is equals to y of dash, or you can say u1 dash. So here like this is the initial condition is given, y y at x naught is given here. So if y equals to u1, it means it is given that u1 of x naught equals to b naught. And then from this equation, what we do, we divide by this a naught to the both side of the equation, and then we take all the terms to the right of it, and finally we have this. So this is equals to y double dash. We can obtain this term equation from this equation. And then since we have already assumed y dash equals to u2, so if we differentiate y one more time, so y double dash equals to u2 dash. So it's like u2 dash equals to y double dash, and it's equals to this term. And then we can, if we simplify it, we can rewrite this also. But this is the our second initial condition, y dash of x naught equals to b1, but y dash we have assumed as u2, so u2 at x naught is equals to b1. So you can see that we have reduced our second order differential equation in a first order system of differential equations. And here we have one variable is u1, another variable is u2. So we can rewrite this system of first order differential equation in terms of the matrix form also, like u1 u2, and this dash actually not transpose, it's like a derivative thing. So u1 and u2 like this, and then this derivative is there, and then here we have only u2, so here this is u2 is present, and here we have this f2, but f2 is actually equal to this thing, you can see, and with this as a initial condition. This is the initial condition because here we have u1 x naught equals to b naught and u2 x naught equals to b1. And then we solve this linear system of first order differential equation in place of solving a second order differential equation. So we can reduce any nth order, like if you have nth order differential equation, you can reduce that nth order differential equation into a system of first order differential equations. So in general, like if we write, so like this may we represent a first order system of differential equation, y1 y2 are two variable. So these y are not related to the previous thing. So like they are giving definition of a linear system of first order differential equations. So y1 y2, then its derivative, not transpose, And the term the function involving x y1 y2 and the function involving x y1 y2, this f2x x comma y1 comma y2, and with these two or this as a initial condition. So in if they use like a capital Y or bold Y to represent this, and here now this is a transpose, then f is represented by or capital F you can take, and this is capital B or bold B you can take. Then this system of first order equations 4.9 can be rewritten as this: y dash equals to f of x comma y, and y of x naught equals to b as the initial condition. So first we derive the solution to find the solution of this first order initial value problem, and then those solution can be generalized to the system of first order differential equations. So there are some problem like reduce the following second order initial value problem into the system of first order differential equation. So here this is the first problem: 2y double dash minus 5y dash plus 6y equals to 3x. So and with initial condition y of 0 equal to 1, y dash of 0 equals to 2. So again what they will do, they assume that u1 equals to y and the derivative of u1 equals to another variable u2. So obviously the first condition is y0 equals to 1. So we have u01 equals to 1 as y equals to u1. Then we take u2 dash, but u2 dash is equals to y double dash. So and y double dash from here you can see it is like 3 plus 5y dash plus minus 6y upon 2, and but y dash is our u2, so this y dash is also replaced by the u2, and this y is replaced by u1. So it's like 3 plus 5 u2 minus 6 u1 divided by 2. So like this we have, and then we know that y is u1 and y dash is equals to u2, because u1 dash equals to y dash equals to u2. So this and so this is now can be rewritten as in the system of first order differential equations. Then what we will do in this numerical or iterative methods, what we do, we like this x naught initial point is already given to us, and its value of y is also given to us in this kind of problem. You can see y of x naught is also given to us, and someone asks you to find the value of y at the new point b. So to find the value of y at the new point b, you have to solve this differential equation. So what you will do, because we are doing it numerically, so what we do, we consider the interval from x naught to b and divide the interval into n subintervals. So x naught to b is a one interval, and then we divide this one interval into n subintervals, and and they are divided like a equally spaced. So how we divide, like their common difference, like if you take any xi minus xi minus 1, then you will get h. So we generally take this uniform spacing. Whatever method we will discuss, we discuss for the uniform space. So we divide this given interval into n subintervals, and they are equally spaced. And then from x naught to we calculate x1, then x2, and then xn, and then we finally say this is the value of y at x equals to b. So there are two kinds of method. One is single step method and one is multi-step method. So what we do in the single step method, in single step method, like because here you have already known that we have to divide the given interval into n subintervals. So like y of x naught I know, but I have to calculate y at x1. So if for calculating y of x1 I required y of x naught or x naught value, then this kind of methods is known as the single step method. Suppose like in between you have to calculate the y of x no x2, and for calculation of y of x2 you require the value x1 or y of x1, not the previous. This x naught is not now not desired now when you are calculating y of x2. So to in the process of calculating y of x2 require the evaluation of x1 y x1 like those, then such a method is known as single step method. For multi-step method, like if I am calculating value of y at x2, I may require value of y x1, I also required value of y x2 x naught. So if I required more than one previous terms to the calculation of the y at x2, then such a method is known as multi-step method. So in single step methods, the solution of any point xi plus 1 is obtained using the solution at the previous point xi. So you can say that here the value of y at xi plus 1, that is this one, because this notation are now I think you are familiar, because in the beginning of the course I told you that y suffix I plus 1 means it's the value of y at the point xi plus 1. So we are calculating y at xi plus 1, and this is can be calculated by yi plus h, then phi of xi plus 1, xi plus 1, yi and h. So no previous term like xi plus 1 is sufficient. Before previous terms, before xi plus 1 we don't require anything. So such a method is known as single step method. And why this kind of method is known as, because the evaluation of yi plus 1 in the left involves some evaluation of y in the right also. So such an solutions or method is known as implicit methods. Implicit method, like evaluation of yi plus 1 involve a function of yi plus 1. So such a method is known as implicit method. And then if the evaluation of yi plus 1 required this yi, xi and yi. So it does not require the evaluation of yi plus 1. So if we are using this kind of method, then such a method is known as explicit method. So this is called implicit method because they are involved the evaluation of yi plus 1 to calculate the value of yi plus 1. But here they are not requiring the evaluation of I plus 1 when we are calculating yi plus 1. So this is known as explicit method and this is known as implicit method, and both are single step method. Then we have this multi-step method. So in multi-step method, the solution at any point xi plus 1 is obtained by using the solution at a number of previous points. So suppose we use like yx and y dash at k plus 1 previous points, like xk plus 1, xi plus 1 is required, xi is also required, xi minus 1 is also required, and xi minus k plus 1 is also required in the calculation of yi plus 1. You can see here. So, like we are calculating yi plus 1, and here we require the evaluation of xi plus 1, xi also, xi minus 1 also, like xi and yi minus y plus 1 and yi minus yi and yi minus 1. So here like we are requiring 3 points or like 2 plus 1. Okay, so 2 plus 1 points are required. One is xi, one is xi minus 1, another one is xi plus 1. So 2 plus 1 points evaluations are required in this method. So such a method is called like two-step method. Or if you use all these points, k plus 1 points in the evaluation of yi plus 1, then such a method is known as k-step multi-method. So, and this is like a two-step methods because we are using 2 plus 1 points, like 3 points, previous points in the evaluation of yi plus 1. Then we have this Taylor. So this we will come later on this Taylor. Then we discuss. This is Picard. So substitute this value is very clear to each because we know that the relative energy. So we have this. I think this one is also visible to you. Single step and multi-step methods are already discussed. Okay, so we have discussed this thing. Initial condition. So initial condition, like we are calculating the or we have conditions like y at x naught, y at dash of x naught, y double dash of x naught, and y nth minus 1 dash at x naught. So if this is the situation, then it is known as initial value problem. But instead of this, you have like more than one point, like you have y at x naught, and then y at x1 also there, or y at x2 is also there. Then such an equation or such a condition is known as boundary conditions, and the problem is known as boundary value problem. Like if more than one point is used to describe the conditions. So if more than one points are used to describe the condition, then such a condition is known as boundary condition, and such a problem is known as boundary value problem. So let's discuss this method, Picard's methods. So in this Picard's method, we consider the first order differential equation. So this is our first order differential equation, and with initial condition. So now we are discussing initial value problem. So this is the initial value problem. Let you know that y naught is the value of the y at x naught. It is given to you. So y naught when x equals to x naught is given to you, and you have to solve this equation 1. So this so like what we can do, we keep dy here and take dx to the right, and then integration within the domain of integration, like lower limit is x naught and upper limit is x. Maybe here it is there. Okay, here it is there. So we are, I think this handwritten notes is also visible to, also visible to all of you. So we were discussing this Picard's method. So here we have this initial value problem, dy by dx, first order initial value problem, dy by dx equals to f of xy, where fxy is a function of x and y. And then we have y of x naught equals to y naught. So integrating 1 between the limits x naught to x. So if you do x naught to x, you will get your y is actually y naught to y. Actually, it is not like that. Like like you are integrating with respect to x naught to x in the left also, but you know that here y is actually function of x, so its integration is like yx, because y is a function of x, and then it is like x naught to x, and then it is like y of x minus y of x naught. So this left part. So you are integrating within with respect to x within the domain of integration x naught to x. So obviously if x naught to x, it's y is going from y naught to y. So it's like that. So you will get in the left side y of x minus y naught, and that y of x, you if y of x can be rewritten as y, and this y of x naught is actually y naught, and that we have taken to the right side, and the left side as it is x naught to x f of x y dx. So x naught to x f of x y dx. So this is the, so if we integrate equation 1 within the domain x naught to x naught, we will get the equation 2. So you can see that this is actually explicit form equation 2, because we are calculating y, but we don't know y, and y is required inside also. So how we like solve this one, because this is not because we don't know y, and the integration of and value of y is required in the right side also. So what we do, we substitute some approximate value of y here, and then we will calculate. So as a first approximation of y1 to the solution, we put y equals to y naught in fxy in the integral part 2. That in the right side, we replace the inside y in the y present in inside the integral by y naught. Y naught, what is y naught? Y naught is this given to us. Y at x naught equals to y naught. So we will get the value at x1. So y1 is actually y of x1. So y of x1 is equals to y1 equals to y naught plus x naught to x. This x remain as x. And then you will get f of x y naught dx. Then for second approximation y2, we put y equals to y1 in this first equation itself. So we will not change this y naught. This y naught remains same. You can see this y naught remains same. For to calculate y2, we are changing this y by y1. So we are getting here actually another solution. Not actually, this is not y of x1. This is actually y1x. Okay. So tomorrow, same time, 9 o'clock, we will again. Y1x. So this is actually another solution, y2x. And this y naught will not change. Similarly, y3x is equals to y naught plus x naught to x f of x y2. So we are again changing in equation 2 in the right side y by y2, and continue this process. A sequence of functions of x, like one solution is y1x, one solution is y2x, and one solution is y3x, is obtained, each giving a better approximation to the desired solution than the previous one. So here, like I told you earlier, that y1 is actually y1x. So that concept is not here true. Here actually y1x is itself is a function of x, and this is like a first solution to our differential equation. This one, equation 1. Then y2x is another solution. So here y2x is not y at x2. It is like another solution to the itself a function. Here y1x is a function, and it's a solution to the equation 1, and y2x is also a function of x, and it is again solution to the equation 1. And similarly y3 function is again function of x, and it's a solution to this equation 1. And like this, if we are continue in this way, we'll get a sequence of solutions, and each one is like next one is better than the previous one. Like the value of the error will be less in y2x as compared to y1x. So we'll see one problem. Use Picard's method to obtain a solution up to the fifth approximation of the equation. This with the initial condition that y equals to 1 when x equals to 0. So y at x naught is given to you as 1, and here x naught is equals to 0, and this one is y naught. So y naught equals to 1 is given and x naught equals to 0 is given. So this is your given differential equation. Dy by dx equals to y plus x equals to 1. Sorry, the equation 1. Then we have to integrate within the domain 0 to 1, and then we will have this one. So like they are writing again and again. Now, instead of this, we write some iterative procedure like this yn, or instead of n, I take k yk plus 1 x equals to y naught plus integration x naught, and then x, and then f of x comma y k, even though it's again a function of x dx. Actually, this is the general formula we remember for the Picard's iteration method. So we are not going to integrate each and every equation and try to get this form every time. We just remember this thing and identify what is f, what is y naught, what is x naught, and substitute the value. So you can see here, if I go, this is like y naught, and this is like x naught, because this is x naught, so x naught to x, and this is like f of xy. So y equals to this, and then finally this is the solution they have assumed, like y1 x equals to y naught is 1, then plus integration x naught to x, and there we require the value of f x at y naught. So what is f x y naught? Because here this whatever is like other than this in the right side of this dy by dx is equal to f of xy. So if in this f of xy I will write f of xy naught, so obviously it is like x plus y naught, and this is like x plus what is the y naught value, 1. So I have substituted here x plus 1, I substituted here. So from we are integrating x naught to x naught to x, 1 plus x, because f of x y naught is x plus 1, and I am getting after integration 1 plus x, I am getting 1 plus x square by 2. Next, to calculate the value of y2, so I require the value of y of x y1. So y of x y1, I again see the definition. This is actually my f of x y. This is f of x y. So here I substitute x equals to x and y equals to y1, y equals to y1, and then I substitute the value what I obtained in the previous step for y1. Y1 is this one, 1 plus x plus x square, and then after simplification these values, even though they are directly substituted here, 1 plus x square by 2, actually this in y1 it is x square by 2 plus x. So this value, this is actually this f of x y1, and then I am integrating from x naught equal to 0 to x, and this is my y naught. So I am using this equation each and every time to get the next better value of y2 or ykx, and then I integrate it. So after integration, because